guys, it's Farnaz, and we're going to be running through Exam 2, 2012, and the first question is asking to arrange the molecules based on increasing solubility in water. Now, what do we know about water? Water is a polar molecule, and we know from general chemistry and also from organic chemistry, like dissolves like. So you're going to want to look for a molecule that's given that is polar. Now, what do you know about a hydrocarbon chain, like choice number 1? A hydrocarbon chain is purely based on hydrogens and carbons, so there's no real polarity in that. So the hydrocarbon chain, so this one is going to be the least soluble, so you could remove those. Now, when you have an ionic bond, so anything that you see is a positive species interacting with a negative species, that's going to be able to easily dissociate in water. So that is going to be the most soluble, and your answer is B. Question number 2 is asking, whoops, sorry, technical difficulties. Okay, so question number 2 is asking to pick which one of the pair is the most stable. And what we're going to want to do for this is draw each choice out in the chair conformation. Okay, now in the chair conformation, you want to give the big groups the equatorial position because that's going to minimize the steric hindrance. So when you have a molecule like this, which is trans molecule, where one is on a wedge and the other is on a dash, so when they're opposite of one another, that's going to be trans. So right here we have this methyl group in the down position. And by down, I mean it is the lower bond. So when you have one already in the down position and you're dealing with the trans molecule, the Br, which is trans to the CH3, is going to want to be in the up position for it to be trans. So 2I. Okay. So we're going to do the same thing here, and we're going to put the CH3 in the equatorial position, but here we have a molecule that's cis, and when this methyl is in the down position, since the molecule is cis, the Br also has to be in the down position, which then forces the Br into the axial position. Now, which one of these two is most stable? The most stable one is going to be this. Why? Because here you have 2 in equatorial, and here you have 1 in equatorial and 1 in axial. And equatorial is always going to be more stable than axial. Okay. Now, again, we're going to draw the methyl in the equatorial position, and here we have a molecule that is cis. So since this methyl is in the down position, the Br is going to also want to be in the down position. So here is up, and here is down. Okay. And again, CH3 in the down position, and the Br, since this is trans, your methyl is in down. Since it's trans, the Br now has to be in the up position, so the Br is going to come like that. Now, which one of these two is the most stable? The most stable one is going to be 3, because here, again, you have 2 equatorial, but here you only have 1 equatorial and 1 axial, so this is going to be the more stable molecule. Okay, So what do we know about enantiomers? Enantiomers are non-superimposable mirror images. So we're literally going to take these molecules and we're going to draw the mirror image of them and see what we get. So let's start with A over here. So that's OH. OH. So these are dashes, and that's on a wedge. So this is my mirror plane, and I'm literally just going to pretend that I have a mirror up against it and draw the mirror image. So this here is going to be wedge. It's going to correspond with that. This here is going to remain dashed. And this here is also going to remain dashed. So now if we look at this, we see that this answer that we got is right here. So the trick to doing this is, especially if you don't have a models kit, is assign R and S. RS, the enantiomer of it is going to be SR. So the stereochemistry of it is going to switch. So when dealing with this one here, let's determine R and S. So the fluorine is going to be 1, this chain is going to be 2, here is going to be 3, and that hydrogen is going to be 4. So that is the movement. So this is an R. A nice little trick to remember R and S is R, the arrow goes this way, S, the arrow goes that way with the top curve. So now let's assign R and S to this one here. So you have 1, 2, 3, 4. So this moves in the R direction. But you have to be very careful because this technically is not R. This trick with numbering to determine if it's R and S only works if the hydrogen is in the dash position. So here right now you see that the hydrogen is in the wedge position. So literally what you're going to do is you're going to calculate R and S. Whatever you get, you're going to switch it. So that is going to be S. So this molecule right here is RS. Is this. So we're just going to do the same exact thing, and we're going to determine R and S. This is 1, 2, 3, 4. So it's going to move in this direction, which is going to be R. But remember what I just said over here, your hydrogen has to be in the dash position. So you're going to change that into an S, since it's not. And then you have 1, 2, 3. Which is S. But you are going to encounter the same issue where you need to switch that to an R. So here you have an S, R. So this molecule is an SR. And remember what we just said, when the enantiomer of something that is RS is SR. So this is enantiomers. Now let's say if it was identical, RS would also be RS in the molecule below. If it's a diastereomer, you would only change one of them. So RS would either be RR or SS. So you're only going to be switching one stereo center. These questions. So you want to find the equilibrium constant of this, and all they're giving you is the amount of energy. Now, if you remember in general chemistry, they gave you an equation. It was delta G equals delta G0 minus RT ln of EQ. Okay, so this is a shortcut equation. Whenever you see something like this, use this equation. The delta G that you're going to plug in is the 3.8. So it's going to be 10 to 3.8 divided by 5.6. And when you do the approximation value for that, you get D. Question 6. So relative to the chair conformation, the boat conformation of cyclohexane is destabilized by. So this is literally something that you should just know and write in your card. The boat conformation has a lot of steric strain and a lot of torsional strain, so that's going to be F in order of increasing stability. So remember what we just said, equatorial, always most stable position. So which one here is equatorial? That has an equatorial position. So this here is equatorial, this and this is equatorial, and this molecule has no equatorial at all. So you know that 2 is going to be the most stable, and 1 is going to be the second most stable, and 3, since it's going to have both of their side groups in the axial conformation, that is going to be very, very, very unstable. So your answer is going to be F. Okay, so this again is something that you would write on your card. And the planar, the reason why you draw something in a chair, while you draw a cyclohexane, in the chair conformation, is because you want to get rid of that angle strain. You want to get rid of the angle strain and also the torsional strain. Okay. How many stereocenters does this core structure have? So you're literally just going to count the stereocenters. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is 9 stereocenters. Which of these following compounds are meso? So meso molecules are molecules that do have stereocenters, except they are still, although they have stereocenters, they are achiral. So that just means that they don't rotate in plane of light. And the way that you determine if something is meso is you try to find a plane of symmetry. Now, this molecule has a plane of symmetry running down the middle right there. So, you know, 1 is meso. Now, if you do the same thing with this one, and you try to fold it over, you have a wedge here and a dash here. So that is not symmetrical, and you could cancel that out. And no matter what you do with choice 3, you can't make that symmetrical, so that's out. Now this is where it gets a little bit tricky, where you are going to want to have your groups on the same side. So I'm going to want to put these BRs on the same side, as in I'm going to want to put them both in the planar position. You could choose whichever want to put in the planar position. If you have a models kit, this is really, really handy. So when you move the BR down into the planar position, the CH3 will move into the dash position, and the hydrogen is going to go into the wedged position. Now, if you see with that rotation that we just did, you have a plane of symmetry running through the middle. So 4 is also meso, so your answer is going to be F. Okay, so give the structure of 7-bicycloheptane. Okay, so you know that there's going to be 7 carbons because it says heptane and there's not going to be a double bond. So this this is written out like that, the first two numbers usually correspond with how many carbons are are on the sides, and the last number, so the 1, is usually how many carbons are in the bridgehead. So this, since it's 7, you have 7 carbons. You have 1 carbon here and 1 carbon here because it says 2, and you have 1 carbon here and 1 carbon here because it says 2, and then you have a single carbon in that bridgehead. So you're going to want to connect these together, and your bridgehead is going to be over here, and that has a single carbon in it, and that's going, when you number that, you're going to number from 1, 2, 3, 4, 5, 6, and that top carbon is going to be 7, so you know that's where the Cl is going to go. Draw the most stable conformation of trans-1-tert-butyl 3-methyl-cyclohexane. Okay, so with this, you're going to want to draw the planar conformation first and then take it from the planar into the chair conformation, because chair conformation is going to be the most stable conformation for that. So this is my cyclohexane, and I have 1 tert-butyl. So I have a tert-butyl coming off on carbon 1, and I have a 3-methyl, so this is carbon 1, 2, 3, and this is the 3-methyl cyclohexane. But now this is something very important where it says trans, and we just discussed trans is when you give when the two groups are going to have opposite stereochemistry. So I'm going to put 1 on the wedge. So I'm putting the butyl on the wedge. You could do whichever one you like. And I'm going to put that methyl on a dash. And to translate this into chair conformation, and I'm going to put this here, since it's the big group, in the equatorial position. So this is 1, 2, 3. And this equatorial position is also down. And since this molecule is trans, this here is going to have to be in the up position. So it's going to have to come up in axial. And that is going to be the stable conformation, since you have the big group in equatorial, and there's nothing you could really do to make both of them in the stable equatorial position. Okay, so give the structure of a compound consistent with the following properties. Oh, I need IR spectrum up right over here, and it's giving me the molecular formula. So the first thing I'm going to want to do is my index of hydrogen deficiency. So my IHD formula, which was 1/2 2C plus 2 minus H minus X plus N. This is something that you should write on your card because it is a pain in the butt to try to memorize it. So 1/2 times 2 times 3 plus 2 minus 6 minus, okay, okay, so they're giving you the molecular formula, and the first thing you're going to want to do is your IHD. which is 1/2 2c plus 2 minus h minus x plus h. And you're going to solve. And when you plug these values in, you're not including the oxygen, by the way, you're going to get an IHD of 1. So you know there has to be a double bond or a ring somewhere in the molecule. And it's telling you that it is optically active and rotates in polarized light. So you know that it has a chiral center in it. It has a stereocenter in it, and it's a chiral molecule, meaning that it's not meso, because meso compounds do not rotate in polarized light. And I went over what meso was before, but if you need a little bit of a refresher, meso is when the compound has stereocenters, but it has a plane of symmetry, so it's not going to rotate. And it also says you have absorptions in 320 and 1630. So let's go and look what 320 and 1630 are. Okay. 320 is an OH bond, and the other one was 1630, and 1630 is a C double bond O. So you know you are going to have an OH, so an alcohol, and a carbonyl in the molecule. So let's first draw out 3. Oh, that's 4. Okay. Well, that just messed up. But, okay. So you're going to draw this out. And let's look for the possibilities on what we can do. So I'm first going to put an OH here, and I'm going to put a double bond O there. And this is literally what you're going to be doing when you have when you're taking the exam, and they're most likely going to ask a question like this. You're just going to do trial and error, make a molecule, and see if it fits with all of the criterias. So it does match the molecular formula, but let's see if it's optically active. So here you have a hydrogen, and here you have a hydrogen, and here you have a hydrogen. This molecule is not optically active because this is technically not a stereocenter. Because in order for it to be a stereocenter, it has to have 4 different substituents coming off of that carbon, and you see you have 2 hydrogens coming off. So you know that's not a possibility. But what happens if we try to move that OH into the middle, and let's keep that double bond O where it is? This would be a stereocenter because you have a hydrogen coming off here. You have a hydrogen, a methyl, an OH, and a carbonyl coming off, which is 4 different things. So this here is going to be the molecule that follows all of these criterias. So you have H2PDC, and H2PDC is going to be a reaction that you're going to use a lot throughout Orgo 1, and also if you continue to Orgo 2. And what it does, it takes a C double bond C and takes it into a C single bond C. This is going to be in the front of your cover sheet, so if you don't remember, it's going to be in your library of functions. So we're going to draw out all the possible places to put that double bond. Okay, and one more. Whoops. Okay, now the key part in this question is it says that they want this as the only product, as in you don't want to get any other side products. Now, the issue then is with these three choices, you are going to get a side product. For example, this one, when you use H2PDC, you can get either that methyl in a wedged position, or you can get that methyl in a dashed position. Now, the only one where the H2PDC does not affect the stereochemistry here is when you have the methyl, when you have the double bond away from the methyl group. And when you use H2PDC, you will get this as your final answer. Okie dokie. So, compound A. Okay, so they're giving you a molecular formula. So let's do C5H8O, and let's put that into our IHD. And that's 1/2 2C plus 2 minus H. So you have 10 plus 2 minus 8 divided by 2. And when you do that, you're going to get 2. So you know that you're going to have a ring and a double bond, or 2 double bonds. So let's just remove that. So you have IHD equals 2. Now, this here says you have a molecule that is chiral, that's achiral. So that means it's either going to have no stereocenters or it's going to be meso. And you also have a final product that's achiral. So that's going to mean you either have no stereocenters or it's going to be meso. But the center here, it's going to be a racemic mixture. So when something is a racemic mixture, that means it's going to be a mixture of enantiomers. So when we look into the IR spectra for 1704, okay, so that's going to be like either a ketone or an aldehyde, because that is for a carbonyl. So you're going to want to draw something that's achiral. So I have carbonyl here, and I need a double bond somewhere. So I'm going to put a double bond right over there. And when it reacts with LiCH3, which is basically just a CH3 minus, which is going to come in and attack that carbonyl and push it up, you're going to get a racemic mixture. So when I attack with that methyl group, I'm going to get, I'm sorry, that's not really dark enough. When I attack with that methyl group and add H3O+, I'm going to get a racemic mixture because there's no way to control it. I'm going to get this. So these two steps do fit, these two drawings that we did does fit the two steps. And this is an achiral molecule because as you see, there is no stereocenters. But then when you use H2PDC, which gets rid of the C double bonds O, you go into an achiral molecule. Treatment of the D compound. So treatment of this, okay, I think this actually falls into chapter 6 material, so I am not going to cover it right now. So let's move on. two stereoisomers are the product of the following reaction. Give the number of stereoisomers possible. So the little equation that you need to know is 2 to the n. And n is the number of stereocenters that you have. And right here we have 2 stereocenters. So 2 to the 2 equals 4 stereoisomers. So give the following product in the reaction. So you're going to have, let's draw our curved arrow, you're going to have this negative charge come in, and it's going to attack that carbonyl, and it's going to push it up. And then it's going to give that a negative charge, and the negative charge on this oxygen in the second step is going to become protonated. So as we talked about in the previous question, is that this reaction, it does not have any specific stereochemistry. So when you get that, you're going to get 2 different products. What's different is going to be the stereochemistry of it. Now, it's an important point to remember that, it's an important point to remember that this reaction that you were just doing only affects the stereochemistry of what is being attacked. So it only affects the stereochemistry here, but it leaves this stereochemistry alone because it has absolutely nothing to do with these carbons here. Now, state whether the 2 products you have drawn are constitutional isomers, diastereomers, or enantiomers. Well, we know that they're not constitutional isomers, and we know that they're not enantiomers, and we know they're not enantiomers because while this here and this here is the same, you have a different stereochemistry in these circled areas. So when that happens, it's going to be a diastereomer. Alright everybody, thanks for watching. I hope this helped, and good luck.